This is Heliox, where evidence meets empathy. Independent, moderated, timely, deep, gentle, clinical, global, and community conversations about things that matter. Breathe easy, we go deep and lightly surface the big ideas. Welcome back to The Deep Dive, the place where we take the fire hose of cutting-edge research and distill it down to the essential, fascinating nuggets you need to sound genuinely knowledgeable. Today, we are strapping in for what is perhaps the most ambitious convergence of technologies currently underway: the marriage of machine learning and quantum computing.
That's right. We are diving into the intellectual frontier where, theoretical quantum mechanics meets the practical, messy demands of real-world AI deployment. This isn't just abstract thought experiments. We're looking at the foundational engineering challenges that researchers are solving right now to build the scalable AI systems of tomorrow.
And our sources today come directly from the pioneering work of a collaborative group, including Ratun Rahman, Dinseen Grian, Christo Thomas, Alexander Daru, and Walid Saad. This research really marks a critical pivot point, the journey from, complex quantum algorithms isolated in clean labs to systems designed to function robustly across decentralized networks. We're talking potentially billions of heterogeneous devices globally.
Our mission in this deep dive is sort of structured around two monumental problems they encountered and, solved. First, we explore the deep dive into infrastructure. How do you train a quantum algorithm across a diverse network without everything just collapsing into noise? This led them to develop a robust form of quantum federated learning, or QFL, specifically by conquering the Achilles heel of system variability, something they call heterogeneity.
Right. And then second, once they sort of fixed the infrastructure, they moved on to superpowers. We'll examine how they leveraged the strangest property of quantum mechanics entanglement to enable an unprecedented, almost implicit form of coordination in multi-agent AI systems.
Which is known as entangled quantum multi-agent reinforcement learning, or EQRL. It's really a story of defining the scaling dead ends of current tech and then using physics itself to build a way around them.
So whether you're trying to understand the future of privacy and AI or the next generation of cooperative robotics, this deep dive provides the map to the cutting edge. Okay, let's unpack this by establishing the territory. We have to start with quantum machine learning, QML. If you're familiar with classical machine learning, you know data is processed using binary bits, zeros and ones. QML takes that whole computational concept and integrates it with the truly surreal world of quantum physics.
And that surreal integration is absolutely key. When these researchers started out, they saw the promise of three fundamental quantum phenomena that dramatically change how we approach processing complex data. The first, and maybe the most foundational, is superposition.
Right, superposition. This is the concept that a quantum bit or a qubit doesn't have to be just a 0 or a 1.
Exactly. It can exist as a probabilistic combination of both 0 and 1 at the same time.
Can go spinning coin.
Until it lands, it is both heads and tails. A classical bit is the coin after it has landed.
So a qubit is the coin while it is spinning.
Precisely. And this allows a quantum device to explore countless computational paths in parallel, which dramatically increases the data processing power available in just a single operational cycle.
And that concept alone gives us what they call quantum parallelism. But then we add the really, really strange property, entanglement.
Entanglement. This is where two or more qubits become intrinsically linked. Their fates are coupled. They share a single quantum state. The moment you measure the state of one qubit, you instantaneously know the state of its entangled partner, no matter how great the physical distance separating them is.
The famous spooky action at a distance that Einstein talked about.
That's the one. And when you combine superposition and entanglement, you can harness something called quantum interference, which lets these parallel computations interact to sort of filter out wrong answers and boost the correct ones.
So these properties working together allow for processing of really complex large-scale data. I'm thinking optimization, classification at speeds that classical computers just can't match.
Right. And the devices we have for this right now are often called NISQ devices. That's noisy intermediate scale quantum devices. They're powerful, they're proof of concepts, but they're also exceptionally fragile. They're prone to error, they have limited qubit counts.
And that inherent fragility, the researchers realized pretty quickly, that was the central engineering challenge they had to get over. Okay, so if QML is so powerful, enabling this faster, more complex processing, what was the initial idea? Why not just replicate the classical model, build massive centralized quantum data centers and have everyone upload their data there?
And that was the immediate dead end that the researchers identified. Conventional QML, where all the processing happens on one central server, it might be appealing computationally, but it just hits these insurmountable practical limitations. And the first and most critical issue is privacy. If you're handling high-dimensional, sensitive data like proprietary corporate models, financial records, medical imaging, consolidating all of that into one central server, even if it's encoded quantum mechanically, creates a single, highly vulnerable point of failure.
Right. If that server is compromised, you lose everything. And for applications like, say, personalized medicine or secure government networks, that risk is. It's just
Right.
a non-starter.
It's completely unacceptable. But even beyond privacy, there's the monumental logistical problem of just sheer scale. Imagine trying to transfer petabytes of complex quantum information continuously from billions of distributed devices, sensors, phones, IoT, to one server. The communications overhead would be crippling.
The network would just choke.
It would. Even if the server could process it quickly, the latency and bandwidth would just grind the whole system to a halt. It's not scalable. And that realization was the real starting point for their journey. Centralized QML was a computational marvel, but it was an infrastructural impossibility.
Okay, so that recognition of the centralized dead end led Ratun Raman and his colleagues to look at a successful paradigm from classical AI, federated learning, or FL. Their key innovation was asking, can we make this quantum? Which brings us to quantum federated learning, or QFL.
QFL is a combination of that decentralized, privacy-preserving framework of federated learning with the computational power of quantum computing. The fundamental principle is the same as classical FL. The raw, sensitive data stays local on the client device. Only the learned model updates or parameters get shared with the central server.
So can you walk us through the operational loop of a QFL network? Because the clients are no longer just classical CPUs. They have those fragile NISQ devices.
Okay, so you start with a multitude of decentralized clients. Let's call them specialized quantum edge devices. Step 1, local data encoding. The clients take their classical raw data and immediately transform it into a quantum state using methods like amplitude or phase encoding. The raw data never leaves the device.
So the device is like a rapid-fire data transformer, securing the information right at the source.
Yes, exactly. Step 2, local quantum processing. The client then uses its local quantum processor, its VQC, which we'll get to in a moment, to train a local quantum model. It leverages superposition and entanglement to extract these complex features and patterns from its local dataset, achieving a much better local learning outcome than a purely classical device could.
And then when that local model is optimized, it needs to contribute to the collective intelligence.
That's step 3, communication of updates. Instead of sharing data, the client sends improved model parameters, or sometimes the quantum state itself, back to the central server. That's step 4, global aggregation. The central server, which might also be quantum-enabled, aggregates all these distributed updates using complex quantum algorithms to synthesize a unified, improved collective model.
So the core benefits become dual purpose and really compelling. You solve the scaling problem and the privacy problem of centralization.
And you inject quantum-level computational power into the network.
Exactly.
Absolutely. QFL protects data privacy because raw information is never transmitted, which mitigates that single point of failure. And at the same time, it harnesses quantum capabilities for faster processing and better handling of complex data. This makes QFL a crucial leap for tackling large-scale problems in sectors that need high data security, like defense, finance, and medicine.
To really appreciate the difficulties these researchers faced, we need a quick dive into the specialized tools the clients are using. We know the qubit is the fundamental unit, but how do they actually make it perform computations?
They manipulate qubits using quantum gates. You can think of these as the fundamental reversible logical operations. They're the building blocks of quantum circuits, kind of like the AND or OR and NOT gates in a classical computer. We use gates like the Pauli X, which is like a quantum NOT, the Hadamard or H gate, which is essential for creating superposition, and the CNOT gate, which is critical for generating entanglement between two qubits.
Okay. And in classical deep learning, we organize these operations into layers, neural networks, where weighted inputs are processed. What's the quantum equivalent of that computational layer?
That would be the variational quantum circuit, or VQC. This is the quantum analog of a neural network layer. The VQC is built from two types of gates. First, you have parameterized gates like Rx, Ry, and Rz, which essentially rotate the quantum state of a qubit. These rotations are controlled by numerical angles that act as the trainable weights of the network.
Ah, so those rotational angles are the parameters the client is trying to optimize locally, which will eventually be sent to the central server.
Exactly. They are the trainable knobs of the whole system. The second type of gate is the entangling gate, usually the CNOT, which mixes the quantum information between different qubits. A VQC just stacks these parameterized and entangling gates into layers, and the entire circuit is optimized using classical techniques like gradient descent. This is how the model learns.
But before the VQC can learn anything, the data has to be transformed. That's quantum encoding. How does classical data, a vector of numbers, an image pixel, get converted into a useful quantum state?
Encoding is that crucial first step. It transforms the classical data into a quantum state. And there are different strategies, each with its own trade-offs. Amplitude encoding, for instance, maps the data points to the complex probability amplitudes of the quantum state, which allows for a very compact representation.
And there's also phase encoding.
Right, which maps the data to the quantum state's phase shifts. The choice here is really vital because it determines how efficiently the VQC can even process the data. If the encoding is core, the VQC is essentially flying blind.
And that leads us to the communication bottleneck, sharing the model. You mentioned two ways, and that feasibility really defines the current technological landscape.
That's right. The first is the classical channel approach. This is the practical, near-term solution. The client does its VQC training, extracts the optimized parameters, those rotational angles, and transmits them as classical data to the server. The server then just averages them using an algorithm like FedAv.
It's robust, it works with existing networks, but it's got a major drawback.
A huge one. By converting the quantum state to classical parameters, you strip away all the quantum correlations, the superposition and entanglement that might have contained really crucial information.
You lose the quantum secret sauce on the way up to the server.
Precisely. The second path is the quantum channel. This is the theoretical ideal. The direct transfer of the actual quantum states, qubits themselves, via highly secure quantum communication or teleportation. This preserves all the quantum coherence and correlation, which should lead to better global model performance. However, this is the fragile path. It demands perfect, high-fidelity quantum connections, consistent entanglement distribution, and minimal noise conditions that are extremely difficult, if not impossible, to maintain outside of a controlled lab. And this inherent reliance on homogeneity and perfection is what the researchers realized was the core infrastructural dead end.
So the journey to scalable QFL hit a massive roadblock when the researchers looked past the theory and into the reality of distributed computing. The entire QFL framework, like most initial quantum models, was built on this, well, flawed assumption that every client and every data set is homogeneous or perfectly identical.
And as the foundational work by Raman, Nguyen, Thomas, and Saad really highlighted, ignoring real-world variances is fatal. In the real world, devices are diverse, data is messy, and environments are noisy. This variability is what they call heterogeneity.
And this heterogeneity causes catastrophic instability in training.
Oh, it leads to model divergence, where individual models pull the global model in opposite directions, agonizingly slow convergence, and ultimately a global model that performs suboptimally. When you can't trust the input, you just can't trust the output.
Let's clarify something for the listener. We deal with heterogeneity in classical federated learning all the time. Agents have non-IID data, so non-independent and identically distributed, but their models fundamentally operate in the same mathematical space.
That's a crucial distinction. In classical FL, models share a common language, the Euclidean parameter space. Updates are just vectors of numbers, and FedAv works by simple arithmetic averaging. In QFL, however, heterogeneity doesn't just affect the statistics, it affects the underlying physics.
The physics.
The physics. When quantum states differ, the updates interact within the Hilbert space, which is this abstract mathematical space where quantum states live. When heterogeneity strikes, you end up with quantum states that are fundamentally incompatible.
So this is our deep dive's first major aha moment. Heterogeneity in QFL is a problem of physics, not just a statistical nuisance.
Exactly.
Okay, let's break down the sources of this physical problem, starting with the data itself. Even if all clients are trying to solve the same problem, their input data can be represented in radically different ways.
Got it. This starts with heterogeneous quantum encoding. One client might use amplitude encoding, optimizing for compact data storage, while another might use phase encoding, optimizing for speed. These choices result in totally distinct ways the quantum information is structured. The quantum states from these two clients might not be mathematically compatible at all.
But what if they all agree on the same encoding method? Say every client uses amplitude encoding. Doesn't that solve the problem?
Unfortunately, no. And the research showed this pretty clearly. Even with identical encoding methods, slight differences in the client's local classical data varying normalization, different noise levels, pre-processing steps, will still yield distinct quantum state distributions between clients.
And here is where the physics lesson gets truly astonishing. If client A and client B both encode what is classically the exact same input vector, the result can still be two non-orthogonal quantum states.
That's the core of the Hilbert space mismatch. Since the probability, amplitudes, and phases of the quantum states differ, their updates reside in incompatible quantum bases. Trying to perform a simple Federated on the resulting parameters becomes theoretically meaningless. It's like trying to average apples in the color red. They're fundamentally different kinds of data.
That puts an immediate stop sign on naive QFL scaling. You can't just average. And the complexity only increases when we introduce multimodal data across devices.
Correct. We're planning for a future where some clients might be specialized quantum sensors, generating complex entangled pairs, while others are just processing classical images or text. The variation in input type, quality, and modality complicates the global model integration profoundly. Noise specific to one modality, say decoherence on an entangled sensor, will skew the entire global model and dramatically increase communication overhead as the server tries to figure out how to integrate these incompatible noisy inputs.
Data problems are bad enough, but the reality of NESQ devices introduces a whole other level of heterogeneity related purely to the hardware.
This is system heterogeneity, and it starts with the design of the parameterized quantum circuits, PQCs themselves. Quantum hardware right now is incredibly constrained by qubit count, coherence time, and gate quality. Therefore, clients customize their PQCs based on these very real limits.
Which means a client with high-quality, stable hardware can run a deep PQC with many layers and high expressivity.
While a client with a cheap, noisy edge device might be limited to a shallow PQC with minimal layers. The consequence is immediate. The models are structurally different. You cannot directly average the parameters from a 10-layer circuit with those from a 3-layer circuit. The dimensions don't match up.
And this structural difference is tied directly to the varying number of qubits available to each client.
Exactly. Fewer qubits means lower computational capacity and an inability to adequately represent high-complexity data. And critically, it also guarantees inconsistent parameter size and quantum state dimension between devices. This mismatch forces the server into these complex reconciliation tasks, leading to major communication overhead just to figure out how to merge these incompatible structures.
But the most existential threat to distributed QFL is the inherent quantum noise we mentioned earlier. This is device-specific, it's unavoidable in NISQ devices, and it differs fundamentally from classical computational errors.
The primary culprit is decoherence. This is the process where a qubit loses its precious quantum state, its superposition or entanglement, due to interaction with the environment. Heat, stray photons, vibration, you name it. Unlike classical signal corruption, decoherence is the irreversible destruction of the quantum information itself.
And since hardware quality varies wildly, the rate of decoherence, the speed at which that information is destroyed, varies across the entire network.
Precisely. Clients with higher decoherence rates, maybe due to less effective shielding or cooling, contribute parameter updates that are fundamentally noisier and less reliable. These updates just diminish the global accuracy because they are based on corrupted quantum calculations.
Then you have gate noise and fidelities. This is noise introduced during the actual computation when the quantum gates are applied. A gate with low fidelity is more likely to introduce an error with every single operation.
So if a client relies on low-fidelity gates, it consistently pumps error-prone updates into the federated pool, introducing fundamental computational differences that classical federated learning just never has to face. This is the messy reality that forced Ratun Raman and his team back to the drawing board. They had to engineer resilience.
So the researchers' next step was defining a structured layer-by-layer defense against this onslaught of heterogeneity. Their mitigation framework recognized that, no single fix would be enough. They needed a strategy for the data, the model architecture, and the hardware noise all at once.
This structured approach is what truly separates their work from previous theoretical QFL attempts. They started at the encoding level, targeting that Hilbert space mismatch. The goal here is to align the input distributions before training even begins.
How do you even attempt to align quantum distributions? That sounds incredibly complex.
It is. One approach is encoding harmonization pre-processing the classical input rigorously to standardize it, or even creating synthetic quantum states to represent missing data types. But the more powerful technique is encoding-aware weighting. Instead of weighting a client based on how much data it has, you weight it based on the similarity of its quantum state representation to a global reference state.
So you're basically saying, how weird is your data representation compared to everyone else's?
Pretty much. The formula they use mathematically penalizes models whose quantum state representations are too different. So if your data is weirdly encoded, your contribution is automatically reduced. It prioritizes quality of representation over sheer volume.
Okay, that makes sense. Moving on, how do they handle the architectural differences, the shallow versus deep PQCs?
That's the model architecture level. They tackle these structural differences head-on. Layer-wise PQC aggregation is the pragmatic solution. The server only averages parameters from layers that are structurally shared by all participating clients.
So it effectively ignores the unique, deeper layers of the more powerful devices.
It does, which seems like a sacrifice. But they counter this with qubit-aware embedding. This is a mathematically elegant way for a client with a small number of qubits to embed its lower-dimensional quantum state into the larger global Hilbert space. This allows the small client to contribute an update that is structurally compatible with the deep model without losing its local quantum expressivity. It's a remarkable piece of quantum engineering.
Next up, the hardware-aware solutions, which address resource scarcity and power imbalances.
Right. For clients with minimal resources, they propose hybrid quantum classical integration. These clients can delegate complex, large-scale processing to a robust classical layer while still using their fragile quantum circuits just for fast feature extraction or encoding.
So even the low-powered devices can participate meaningfully.
Exactly. And at the same time, they use fairness-aware weighting, where contributions are scaled not just by data, but by verifiable hardware capacity, like qubit count or known gate fidelity. This stops a single high-fidelity device from dominating the learning process.
And finally, the critical defense against the physics problem, the noise-resilient strategies.
Here, the goal is to fight the decoherence in gate errors. Noise-aware aggregation mathematically weights clients based on the inverse of their noise variance. So a device with very high known noise contributes almost nothing, while a stable, low-noise device contributes the most. It's a much more sophisticated replacement for simple averaging.
And this leads us directly to their primary innovation.
Sporadic participation.
Sporadic Personalized QFL, or SPQFL. This is the protocol developed by Raman and his team that successfully integrated many of these concepts to jointly tackle the two biggest practical hurdles, quantum noise and non-IID data distributions. This is where their theoretical work becomes tangible engineering.
The SPQFL mechanism refines the local training process by adding two crucial terms to the standard training rule. The first term enforces personalization. It uses a regularization coefficient, lambda, which acts like a flexible tether. If lambda is high, the client is strongly encouraged to customize its model for its unique local data, maximizing its local performance.
But if it's low, the model is kept closer to the global structure.
Exactly. So the client gets to retain its local relevance, but lambda prevents it from drifting so far away that it becomes incompatible with the collective goal. Of course, if lambda is too high, the client model can become over-personalized and clash with the global model, so it's a critical tuning point.
And the sporadic component, the key quality control mechanism designed to fight noise.
This is the genius part that tackles the noise problem. After a client completes its local training cycle, the model is subjected to a quality assessment. Crucially, aggregation is conditional. Only clients that meet a predefined validation accuracy threshold, tau, are allowed to submit their updates to the server. This threshold acts as a quality gate.
So if a client's model is noisy or unstable or just didn't perform well, maybe because its local decoherence rates were high or its data quality was poor, it's blocked from contributing to the global model.
Precisely. It's sent back to the device for further local refinement, preventing that bad apple from polluting the global aggregation. This selective participation ensures that noisy or subpar updates are dynamically suppressed, maintaining the integrity of the shared model far better than any naive averaging scheme.
This is a major paradigm shift. Classical FL sort of assumes participants are generally good actors. SPQFL assumes noise and error are inherent and builds a firewall against them. What was the payoff?
The empirical success was significant and consistent. When testing SPQFL against regular QFL baselines, they found consistent accuracy gains. For instance, on the Caltech 101 dataset, a common benchmark for image classification SPQFL delivered a 6.25% improvement over the regular QFL baseline.
Wow.
It demonstrated that by intelligently engineering resilience against the physical realities of quantum hardware and messy data, they could finally make QFL a viable, robust technology. The journey from the homogeneity assumption to noise-resilient reality was complete, at least for distributed training.
Okay, so we've established how to robustly train a quantum model across a diverse, noisy network with QFL. Now we pivot to the truly revolutionary goal, using those trained quantum models to make collective, cooperative decisions in dynamic environments. This shifts our focus from training infrastructure to the application of quantum power in multi-agent reinforcement learning, or QMRL.
Right, if you think of classical reinforcement learning, a single agent learns a policy to maximize its reward. In multi-agent reinforcement learning, or MRL, you have several independent agents, like a robotic swarm, traffic lights, automated financial traders, who must collaborate to achieve a goal in a shared environment.
And the classical solution to this collaboration problem is often the CTDE model. Centralized training with decentralized execution. The agents act on their own, but during training, a central server coordinates their learning process.
That coordination is the critical choke point. Classical CTDE relies heavily on communication. Agents have to constantly share their local observations, their limited sensor data, or they share global networks or shared replay buffers. All of this information is shuttled back and forth through classical communication channels.
Which immediately creates the scaling limitations we saw earlier. Massive communication overhead, privacy breaches from sharing sensitive local observations, and huge computational complexity on the central server trying to fuse all that information.
Precisely. And this structural limitation led Alexander Daru and Walid Saad to pose a really profound question. Why are we still relying on classical communication channels for coordination when we have the ultimate communication medium at our disposal? Can quantum entanglement be the actual mechanism for coordination?
That is a staggering pivot point. They moved from seeing quantum mechanics as just a faster calculator to seeing it as the structural glue of the entire system.
They realized the historical gap. Previous QMRL attempts had just swapped out classical neural networks for quantum ones, the VQCs. But they were still using all the old classical protocols for sharing information. They were just drop-in replacements, completely ignoring the potential of the quantum channel for communication or coordination itself.
And their solution, EQRMRL, Entangled Quantum Multi-Agent Reinforcement Learning, is the first framework to break that pattern.
It's the first to leverage that intrinsic quantum link.
Okay, let's ground this idea. Entanglement is the intrinsic linking of behavior, regardless of distance. How does the Daru and Saad framework use that spooky action at a distance to help agents coordinate without explicit chatter?
Their novelty lies in implicitly coupling the local learning processes. The framework is built on the established actor-critic framework. The agents are decentralized. They each have their own local policy networks, the actors, which decide what action to take, and they each hold a decentralized branch of the value function estimator, the critic, which assesses how good a situation is.
And the central server, the trusted orchestrator, is responsible for creating this quantum coupling device.
Correct. The key innovation is the entangled split critic. The process begins with stage 1, joint input entanglement. A trusted central server, which doesn't need the agent's observations, prepares a highly specific entangled input state. They actually found that a variation of the Bell state, the Psi plus state, was optimally effective for this.
Why that specific state?
The Bell states, especially in Psi plus $, represent maximal entanglement. Think of it as creating a perfect instantaneous communication link between the agents, a kind of shared mental connection that transcends distance. By preparing this maximally entangled state across the agent's input qubits, the server fundamentally and physically couples the decentralized VQC branches of their critics before any data is even processed.
Okay, so the server sends out this coupled input state via the quantum channel to the agents. What do the agents do next?
Stage 2, decentralized encoding. Each agent receives its assigned entangled input qubits. It then takes its local environment observation, its limited field of view, its specific sensor data, and encodes that classical observation using its VQC critic branch, applying it directly to those already entangled input qubits.
Whoa, so when Agent A applies its local VQC to its half of the entangled pair, that operation immediately and implicitly influences Agent B's quantum state. Even though Agent B is encoding its totally different local observation at the same time, the coordination is happening at the subatomic level.
That is the essence of EQMRL. The quantum correlation acts as an implicit coordination signal. Then comes stage 3, joint measurement. The resulting qubits are transmitted back via the quantum channel to the central server. The server performs a joint quantum measurement to estimate the joint value function, which represents the collective state of the whole system.
The payoff of this structure is monumental, especially in terms of data hygiene and privacy.
It is. By using the entangled input qubits to couple the local observation encoders, the system eliminates the need for agents to explicitly share their local environment observations through classical means. This drastically reduces classical communication overhead, improves privacy, and bypasses the bottleneck that plagues classical parallel systems. The complex classical task of aggregating diverse data is replaced by a single, instantaneous quantum measurement.
The elegance of the EQMRL architecture is clear, but the empirical results from Daru and Saad really validate this as a breakthrough. Let's look at the measurable gains in performance. How did it do on speed and stability?
They benchmarked EQMRL in what are called POMDP environment scenarios where agents only have limited, incomplete views of the world. In these complex conditions, EQRL achieves significantly faster convergence. It learned the optimal policy up to 17.8% faster than the quantum fully centralized baseline. The entanglement doesn't just link them, it accelerates their collective understanding of the environment.
That implicit coordination must allow them to explore the state space much more efficiently. What about stability, though, given the inherent fragility of quantum systems?
That was another crucial finding. When testing tasks like the multi-agent cart-pull environment, EQMRL exhibited superior stability, demonstrably lower variance during training compared to the centralized quantum baseline. It's highly counterintuitive, but the results suggest that the maximal input entanglement acts as a strong stabilizing force, anchoring the decentralized network and counteracting some of the inherent NASQ noise.
Okay, now let's get to the most important metric for real-world deployment: scalability, which comes down to resource efficiency. In classical split learning, the central server has to run a large neural network just to merge the agent's input vectors. As you add agents, that central network just explodes in size, right?
That's the classical scaling nightmare. Every agent adds complexity to the central merger network. This is the structural reason why classical systems hit a wall. In EQMRL, the situation is radically different. Because the coordination is handled physically, via quantum coupling and joint measurement, the central server's computational burden is nearly constant, regardless of the number of agents participating.
And the data point illustrating this is staggering.
EQRL required a constant factor of 25 times fewer centralized parameters than the classical split learning baseline.
25 times.
That 25x reduction is the ultimate argument for quantum-enhanced coordination. The complexity shifted away from classical network size and into the quantum physical realm. The central server only needs one trainable parameter tied to the measurement observable. Whether you have 2 agents or 10 or 100, the centralized computational complexity remains minimal and constant. This completely solves the scaling problem.
Wow. They basically replaced a massive, explosively scaling computational network with a single, stable quantum physical operation.
That's it.
So to see this success in action, let's look at the benchmark they used for complex cooperation: mini-grid navigation. Can you describe this environment for us?
Mini-grid is a challenging environment. It's a grid world where 2 decentralized agents are given a common goal. They operate under extreme partial observability, meaning they only have a tiny 7x7 field of view. And to make it harder, they get reward penalties for wasting steps, for turning, for standing still. The key challenge is for the agents to coordinate their search patterns efficiently based only on their limited local information.
So if agents can't coordinate, they should spend most of their time just bumping into walls or spinning around, braining through their reward budget.
That's exactly what happened to the classical and the quantum centralized baselines. Their average rewards clustered near a low negative value. The systems were essentially paralyzed by the lack of global information.
And the entangled system, EQMRL.
The implicit coordination was revolutionary. EQRL achieved an average overall reward 4.5 times higher than the baselines. The agents learned efficient, coordinated goal navigation almost immediately. And critically, EQMRL traversed to the goal 50% faster than the fully centralized classical baseline, and it did this without the agents ever having to share their sensitive local observations.
This confirms the hypothesis, then. The intrinsic, implicit coordination provided by entanglement significantly enhances the ability of decentralized quantum policies to learn cooperative strategies, even when information is highly limited. It proves entanglement isn't just a physical curiosity, it's the most efficient coordination mechanism we can currently imagine for decentralized AI.
So we have journeyed from the theoretical promise of quantum machine learning through the hard-won engineering battle against physical reality. We saw Raman and his team define and conquer the scaling limitations of QFL infrastructure, the massive heterogeneity arising from data, system structure, and quantum noise using smart, noise-resilient protocols like SPQFL.
And then we witnessed Drew and Saad transition from fixing infrastructure to unlocking true quantum power, leveraging entanglement itself as the medium for implicit coordination in EQMRL. By coupling the critics through that maximally entangled input state, they created a system that is demonstrably faster, more stable, and most importantly, vastly more resource efficient due to that constant 25x parameter reduction, ensuring privacy by design.
These works are not isolated theoretical exercises. They are the blueprints for how implementable, scalable, privacy-preserving AI systems will operate in the quantum future. The common thread in this research journey was the intellectual courage to define the limitations, the homogeneity assumption, the reliance on classical communication as the fundamental dead ends, and then to use the core properties of quantum physics, superposition, VQCs, entanglement, to forge entirely new solutions that deliver superior performance and efficiency.
This research has fundamentally shifted the timeline for practical quantum AI, but of course, there are immense challenges ahead. The researcher's success provides the foundation, but the field is still defined by open questions that determine the next generation of deep dives. We'll leave you with the major lines of inquiry currently defining the cutting edge.
First, while EQRL proved efficient for a handful of agents, how will researchers create highly scalable and robust algorithms that function across truly large-scale quantum networks? We need systems that can handle thousands or even millions of heterogeneous clients simultaneously.
Second, the noise problem remains the specter in the room. What advanced error mitigation techniques will be developed to address not just the inherent hardware noise of a single anti-skew device, but also the aggregate systemic errors produced during that complex federated training and aggregation loop, especially when those errors are sporadic and personalized?
And finally, the ultimate challenge of reliability. What protocols are needed to dynamically manage the turbulent quantum network dynamics? This includes the latency induced by decoherence, the outright failure of entanglement generation, or the loss of quantum coherence during transmission. How will network scientists guarantee the stability of these cutting-edge AI systems that fundamentally rely on fragile quantum connections? That's the work that will define the next decade of discovery.
Absolutely fascinating. Thank you for joining us for the deep dive. We'll see you next time.
Thanks for listening today. 4 recurring narratives underlie every episode: boundary dissolution, adaptive complexity, embodied knowledge, and quantum-like uncertainty. These aren't just philosophical musings, but frameworks for understanding our modern world. We hope you continue exploring our other podcasts, responding to the content, and checking out our related articles at helioxpodcast.substack.com.